Okay. I think it's about 3 o'clock now, so we might start our webinar session. Assalamualaikum and very good evening to Prof,
Waalaikumsalam.
Dato, Doctor and all participants. My name is Dr. Fatiha and today I'm going to chair for our third series webinar, which is Advanced Technique and Development or in Biomaterial Characterization and Application. So for today's topics, we are going to have the title Biomechanics and Biomaterial Advanced in Medical Application. So I would like to share, before we go any further, I would like to share some introduction for our speaker today. Right. So today, for the introduction, so today we are going to have a bit special. We only have one speaker for this session. So before any further, this is a little bit brief about our speaker. He's a professor of medical engineering and heads of medical device and technology research group, Meditech, from School of Biomedical Engineering and Health Sciences, Faculty of Engineering, University Technology Malaysia. His career brings over more than 15 years of experience in research, teaching, administration, as well as practicing engineer. He obtained his first degree in mechanical engineering from renowned University Imperial College University and as well as PhD research in medical engineering. So upon completing his PhD in 2005, he joined UTM as an academic staff, and a year later, he established Meditech, which is one of the most successful research group in UTM. At the age of 38, he got his full professorship, which is considered as a young for such significant achievement. In the span of just 10 years, he has secured 95 research grants from Meditech, where he leads 23 of them, and the amount of research grant that he has acquired in over about 9 million in total. Within the same time frame, he has published 254 Scopus Index publication in the field of medical engineering. Out of this outstanding number of Scopus publication, he have 119 of them are listed in ISI Index Journal with a cumulative impact factor 239.780. According to the My Intellectual Property Corporation of Malaysia database of patent from 2001 to 2014, he is the first Malaysian inventor with 27 patents granted. To the date, he holds 35 granted patents and have filed 27 new inventions pending for My IPO approval. Under his supervision, he have 26 PhD students, 31 master by research have successfully graduated in various medical engineering sub-expertise, and he has many years of experience as academic administrator, such as deputy dean with 3 different portfolios such as academic, development, postgraduate and research. And he is also registered as a Board of Engineer Malaysia, has a professional engineer with practicing certificate, and has been appointed as consultant for several companies. And for your information, before he joined UTM, he had working experience as an engineer in Singapore-based and Japanese companies. So here I would like to welcome you, our speaker, Prof. Dato IR Dr. Mohammed Rafiq bin Dato Abdul Kadir. Please, Prof, the floor is yours, and I hope you can share your experience, your knowledge with all of us, the student, the lecturers, and the one that still new, yang masih merangkak to have a stable research. Please, I welcome you, Prof. Dato.
I'll try. Thank you very much, Fatiha. Okay, let me share my slide. Share. Okay, hopefully you can see my slide.
Yes, Dato.
Right, that's great. Now, let's start. Yeah. Bismillahirrahmanirrahim. Alhamdulillahi Rabbil Alamin. Wassalatu wassalamu ala ashrafil anbiya wal mursalin. Wa ala alihi wa sahbihi ajma'in. Rabbi shrah li sadri wa yassir li amri. واحلل عقدة من لساني يفقه قولي ربي زدني علما ربي يسر ولا تعسر وتمم بالخير اللهم لا سهل إلا ما جعلته سهلا وأنت تجعل الحزن إذا شئت سهلا اللهم إني ضعيف فاقوي في رضاك ضعفي وخذ إلى الخير بناصيتي واجعل الإسلام منتهى رضايا اللهم إني ضعيف فقوني وذليل فأعزني وفقير فأغنني وارزقني. Right, okay. Now, before I start, I have a very small laptop. So there is only a screen, my screen here, uh, which is currently displaying my PowerPoint presentation and a small tab showing just 4 viewers at the moment. I'm sure there are more viewers, but because I have such a small screen, so I'm just looking at my slide, and there is a small at the corner there, showing just 4 participants. Right now, I can only see myself and Fatiha and two other viewers. Right now, Fatiha, thank you for the invitation. Yeah, thank you so much for the invitation. It is
Dato, for accepting our invitation as the speaker today.
well, actually, I never turned down any if someone asked me to present, and that someone is from USM, I always try my best to allocate the time. uh, because I have a very, very unique history with USM, USM, because when I completed my PhD back in 2005, I started my research related to biomedical engineering. Unfortunately, UTM doesn't have any medical schools or dental schools, so I have to, find some other universities that offer medical degrees, that do medical research or dental research. And it so happened that the first university that I approached was USM. And that is with the Department of Orthopedics and Department of Orthopedics. So I have almost everybody in the Department of Orthopedics, PPSP, USM. They know me. And I guess that was back in 2000 or 2007, I think. Was it
Okay.
2007? Yeah, long, long time ago. And I think the biodata that Fatiha mentioned just now, read just now, was a bit outdated, Fatiha. Yeah.
Oh, okay. That's what I apologize for that.
Because if I only have 15 years of experience, it means that my age right now is about what, 35, which I'm not.
Because
35.
that one I got from the one that they share inside the apa the different page from the Faculty of Engineering Dato. So
I see. It's okay, it's okay. No worries, no worries. But 15 years of experience means that I'm 35 right now, which I'm not. I'm much older, something like 75 or something. Yeah. Okay. So let's start. Biomechanics and biomaterials advances in medical applications. They asked me whether they can make a video. I said it's okay, no problem, mainly because most of the things that I presented here are the things that I have already published. Yeah. So nothing new, hopefully. Right, let's start with Meditech. Right, and I have about 1 hour to speak to just the PowerPoint slide. Excellent.
okay, no problem Dato. We might have the question and answer. It's okay. Just
Yeah.
take your time, Dato. All right.
Right. Okay.
Okay.
Right. Okay. As I mentioned to you that after I completed my PhD back in 2005, I founded a research group called Meditech in 2006, and that research group focuses on medical implants and devices. We have received more than 15 million ringgit in terms of research grant, and close to 300 ISI publications, 22 granted patents, 42 PhD already graduated, and 36 masters also graduated. So this is just a picture of the team members, yeah, the team members of Meditech. So I'm no longer the head of Meditech because as a research group, even though I initiated the research group, the Meditech research group, the group has since been upgraded into a research center. So now it is called Medical Devices and Technology Center. So Meditech with a C, where previously Meditech with a G, Medical Devices and Technology Group, is now Medical Devices and Technology Center. And the director for the center is the one on the picture sitting on my right. Sitting on my right is Dr. Ardiansyah, Associate Professor Dr. Ardiansyah Shahrum, who is now the director for the Medical Devices and Technology Center. And we have people like Dr. Tan over there, Dr. Nazri Bajuri, Dr. Nida Iqbal, and Dr. Hanif, just a few members of Meditech. Now, what do we do at Meditech? Well, we develop medical devices, and when we talk about medical devices, there are 6 components at least. Biomechanics, biomaterials are just 2 of the components related to medical devices. We also involve heavily in design. Most of the patents that I have are just design of implants. So we study the anatomy, and then we design our own implants. So designing is one part of a job of an engineer, biomedical engineer. So design is one, and then of course, other than design, we analyze our design, and then that analysis part is the biomechanics. And when we talk about medical devices, especially implants, then whether you like it or not, you have to do research on biomaterials. So that's why biomaterials are there. We also have research on tissue engineering. And then we have, of course, manufacturing. And some medical devices also involve electronics. Yeah? So these are the 6 components where all our researchers involved in the research related to medical device. Okay, let's jump straight into biomechanics. We have 2 separate parts, if you like, to this talk. Actually, there are 6. But I removed the other 4 related to manufacturing, tissue engineering, design, and electronics. So the other 4 components, the kind of research that we do in our center, I took out from this presentation. Just look into the biomechanics and biomaterials aspect of medical device. Right. Okay. So this is one of the interesting papers that we published. My PhD student Mina Alizadeh back in 2013, almost 10 years ago. We analyzed a complex spine. Yeah. So this is we try to simulate the thoracolumbar burst fracture. Yeah. And then we try to analyze what happened if we use different rods and crosslinks. Yeah. So you know, rods and crosslinks, you have you can use shorter rods, you can use longer rods. You know, if you the same problem, if you were to show to a different surgeon, they may propose a different option. Yeah. So we said to ourselves, oh, hang on a minute, maybe surgeons cannot play around with the patient, yeah, but we as biomedical engineers, we can play around with this, you know. So we took the CT data sets, we developed the 3-dimensional model, and it is one of the most complex model that we ever developed back then, bearing in mind that that work was about 10 years ago. And then when we talk about biomechanics and simulation in biomechanics, you have to develop not just the 3-dimensional model, you have to mesh it. Yeah, and that is another difficult, extremely difficult part. And then we have to assign material properties. And when we assign material properties, it is not just the cortical bone that we need to assign the properties. We also have to assign properties to the trabecular structure, to the cancellous bone, and then all the soft tissue as well. You know, the kind of material properties that we have to assign to the nucleus pulposus, to the annulus fibrosus. That's totally different kind of material properties because it is not actually hard and solid. And then of course the rod and the crosslinks are not that difficult, but of course we need to make sure that the kind of crosslink that we have match more or less what is happening in the surgical theater. Yeah. So there are 8 altogether, 8 different combinations of the crosslinks, and then we analyze. Yeah. And then, of course, we simulate the extension, flexion, the bending moment of the spine, and we look at the stresses generated at the junction between the nucleus pulposus, between the two vertebrae. There you go. And then, of course, there are facets, articulation, again with a different mechanical properties, and then we can analyze what is the best combination for this particular construction. This is a more simpler one, and we started actually with this one, a simpler one, back in 2012. Just analyzing the different stress distributions and motion for this particular open wedge high tibial osteotomy. And we use 2 very simple implants, which is commercially available. That is the hoodoo plate and the Tomofix plate. So we just compare between the 2. So which one is better in terms of the stress distribution as well as the motion, the micro motion, and of course the stability of the whole construct. Right. Okay. This is a more complex analysis, related to type 3 pylon fractures. And then we validated our predictions with an experiment. When you can see the experiment there, so lots of wires over there. And then we analyzed 3 different external fixators, the delta fixators and the Mikovic fixators, as well as the unilateral, and see how does it perform as far as constructing the whole bone of the distal tibia. Yeah, and then you can see that the tibia itself is not that difficult, but the most difficult part related to this finite element biomechanical analysis are the fractured segments. So altogether, we simulated 8 fractured segments, and of course, when you analyze in finite element, you have to make sure that all these fragments touch each other, yeah, to making it a one giant construct. Otherwise, if there is a gap between these fragments, then we will not be able to transfer the stress, from one section to another section. So this is a very complex analysis on fractured fragments of the distal tibia. And then, of course, we have to simulate the ligament, the tendons, ligament. Those lines, those red lines, are the ligaments, and the other bones of the foot, which is also making the whole construct even more difficult to analyze. But there you go. We managed to get it done. Compared between delta, Mikovic, and unilateral. In terms of results of the analysis that we conducted, it seems like that all 3 of them proved to be worthy to provide stability. And of course, if you can provide certain stability with minimum construct, with minimum rods, with minimum screws, then of course that would be better than having a complex construct. But then again, this is a simplified analysis of the type 3 pylon fractures. There you go. This is comparing two different plates, yes, anterolateral plate and medial distal tibial plate, and looking at the fragments again. As you can see that, complex distal tibial fracture, and we try and analyze using 2 distal plates, distal tibial plate. Cervical corpectomy. Again, the stability after one level corpectomy. So there is one level corpectomy there. Yes, here. So for this particular corpectomy, we analyze various number of screws and plates. So you can see there, we analyze the constraint with 2 screws, semi-constraint with 2 screws, hybrid with 2 screws, constraint with 4 screws, semi-constraint with 4 screws, and hybrid with 4 screws. And then we compare with intact. And these are the segments that we model, cervical number 1 until 7, C1 until C7, and we analyze the displacement. You can see that various displacement there, especially in C2 and C1. And the corpectomy level, it's C4 maintained at a lower level. Next, this is the glenoid, the shoulder joint, and we analyze the number of pegs. Again, so you have a very small part, small implant, the glenoid, and there is not much room, to add more pegs. So if we can make the peg stable with less if you can make the glenoid implant, the glenoid component stable with less pegs, then it is more desirable than having more pegs. So we compare this glenoid implant between the 2 pegs, 3 pegs, 4 pegs, and 5 pegs. Yeah? Again, the implant is this small. The glenoid implant is that small. And the whole idea is to prevent the rocking horse phenomena, because when after you insert the glenoid component, you have, in order to do this, so there is a risk of the glenoid implant loosening. So the pegs are there to prevent any major micromotion. And then we look at the stress and of course the displacement between the 2 pegs, 3 pegs, 4 pegs, and 5 pegs. Knee kinematics, this is another project that we started. We developed the simulator, the knee simulator, and then we test with a standardized knee implant, the femoral component, and then we analyze the design, the geometric variables design. We analyze the mechanism that influence the kinematics of knee implants. This is just a computer simulation using MSc Adams. So these are the results for the kinematics of the knee implants. Okay, this one is related to dentistry. We compare the intrasinus approach versus the extra maxillary approach. So these two surgical approach in various occlusal loading locations for zygomatic implant placement for the treatment of atrophic maxillae. So these are the two approaches, the intrasinus and the extra maxillary. We developed the 3-dimensional model of the skull, and we pick a certain ROI, and then we design the implant, and then we put the implant to simulate the 2 different approaches, the intrasinus and extramaxillary. We analyze using finite element with the loading as shown in the slide there, and then we look at the von Mises stress, under vertical load. So we can see that the extramaxillary approach have more stresses underneath there, compared to the intrasinus. Another of our work on dental post. We are still working on functionally graded materials, functionally graded biomaterials, and that one is for the post. I'll show you later that we have already tried the FGBM, functionally graded biomaterials, for orthopedic for orthopedic applications. But this one, post is, it's a tiny, tiny implant, and then it makes it even more difficult to develop a functionally graded material. So normally they just use either stainless steel, titanium, and so we analyze using computer simulation the post design with different materials. So the post design is either the parallel sided post or the tapered post. So that's the design that we have for the post, and then we vary the materials of the post. And then so we compared 5 different materials: stainless steel, titanium, zirconia, carbon fiber, and glass fiber. These are not functionally graded materials. This is just a standard material that we use, and we can see the stress, the post design stress, and you can see the highest stress on the tapered post with stainless steel material, 26 megapascal. So this is work carried out by Ahmad Madfa, and we publish in Medical Engineering and Physics. This is another project we conducted with University of Hong Kong, Professor Yuka Matindina. We analyze the influence of experimental silane primers on dentin bonding, and we look at the shear bond strength, the morphology, and these are the finite element results that we have. So the finite element results, we take the section, the region of interest of the premolar tooth, and then we section the premolar and we simulate the composite resins, and then we analyze the stresses obtained between various primers and control. We also have a project. This project is with the Institute Jantung Negara, IJN. So we got this data set, and we utilize the data set to automatically segment plaque. So you have the intravascular images, and then from that images you can identify plaque, and then is it possible to automatically segment the plaque? So this is the project that we conducted. It's a purely algorithm based, and we publish in Applied Soft Computing. Right. Now, this particular project on cancellous bone, cancellous bone, we got the cancellous bone. It is bovine, yes, bovine based, not human based. So we collect cancellous bone from bovine, and then we section them and place them inside this jig, special jig that we develop in house in order to create a simple compression test. Simple compression test. So from that compression test, we want to see whether we can actually make a model. We can actually model the fracture of cancellous bone. So you can see that above, the picture above are the picture of the broken cancellous structure, cancellous bone, and underneath the two pictures, the two models, are the finite element model of the cancellous bone. And I believe that we got the model from micro CT scan from one of the agencies, Agency Nuclear Malaysia. Agency Nuclear Malaysia has this micro CT scan equipment, so we went to Agency Nuclear Malaysia. We brought our cancellous bone specimens, and we scanned using that micro CT, and that's how we got this cancellous structure, the finite element model. Again, extremely difficult, and it involves hundreds of thousands of elements in order to construct, and then we compress using MSc.mark. It is an finite element software, and then we look at the fractured segments. And then that particular bone, we test using instron equipment, compress it until it fractures, and you can see clearly this 45-degree fracture site, yeah, for both bone segments. We also utilize the finite element model that we obtained from this micro CT scan to analyze on permeability. And then the reason why we want to analyze permeability is that we want to develop our own simplified cancellous bone, if you like. Yeah? Because cancellous bone is very unstructured, but of course we can measure the porosity and density. But if we can study the permeability of this structure, then perhaps we can develop our own simplified version of cancellous bone. Later, I will show you some of the simplified version of cancellous bones that we developed. So there you go. This is a permeability studies, fluid flow mechanics, fluid flow dynamics. So you can see that we can obtain results for the velocity, for pressure, and flow trajectories inside the cancellous bone. And that bone is about, I don't know, about this size, very small. But we can analyze, develop the 3D model using micro CT scan, and then analyze the fluid flow, flow trajectories. And we compare, of course, with other published results as well. Right, biomedical materials, as I mentioned to you, that Meditech, as a research center, we have one section of Meditech concentrating on biomedical materials, and we have research on metals, polymers, ceramics, as well as the bone itself, the tissue. And just one slide. This one is from Callister material science book, just to show that different processing will give different properties of materials. Different processing will give different properties of materials. And the previous two slides, I showed you the results from compression testing. Now this one is torsional loading. This one is torsion, yes, torsional loading on compressive fatigue behavior of trabecular bone. So we basically modify our instron equipment so that it can do torsion, repeatedly. Yeah, it's a cyclic behavior, and see the fracture sites of the cancellous bone under this torsional loading. And this is interesting because we got quite a lot of significant comments from the reviewers, but fortunately we managed to get this work published in Mechanical Behavior of Biomedical Materials, one of the most difficult journal to publish when you talk about mechanical behavior of biomedical materials. This is the journal. Right, as I mentioned to you that we tried and are still working on this functionally graded biomaterial, FGBM, and this one is one of the successful work that we have done related to FGBM, pure iron with stainless steel. Yes, so we have two parts. So that's the pin. The pin consists of two materials, if you like. Yeah, two different materials. Pure iron on top, and then stainless steel 316L at the bottom. And the way we fuse these two materials are through friction welding. Yeah, friction welding. So it involves a very high temperature. The pure iron rod and the stainless steel 316L rod, we fuse them using friction welding, and so once it is fused, we will have three different material properties. So one rod consists of three different properties. One, the property of the pure iron itself, and the second one is the property of the 316L itself. And of course, when you fuse them, you have this heat affected zone in between these two materials with its own properties. Yeah? So we have various properties and various composition of materials, and we use it as a pin. Um, and we use mice for this particular project, and we can see that the degradation, the whole idea of this FGBM is that pure iron degrades, yeah, but stainless steel 316L does not. Yeah? So we had this crazy idea that perhaps we can make a screw that, you know, once the bone heal, then there is no need for a surgery to remove the implant. So there is no need to unscrew, if you like, yeah, because the part, the pure iron part will get dissolved over time, yeah, and hopefully when it dissolves together with the bone heal, yeah. So the bone heal, once the bone heal and the pure iron dissolve, so you can just take out the 316L with ease. So that's the whole idea. So and then we try this FGBM, uh, and well, alhamdulillah, it works. Magnesium, uh, I don't know, some of the team members are so obsessed with magnesium. I think the main reason would probably be that magnesium is the lightest element on Earth. Yeah, lightest element on Earth that we can use as biomaterials. You know, compared to other bioinert materials like cobalt chromium, that's heavy. You know, titanium, that's heavy. Stainless steel, even heavy. If you can somehow, if we can somehow develop, and some of the team members believe that certainly within the next, you know, 10 or 15 years or so, magnesium, you know, if you can somehow change the properties, coat them, whatever, you know, then magnesium will be used because it is the lightest element that you can use as a biomaterial. But the problem is, of course, magnesium is easily corroded. Easily corroded. So a dynamic degradation of porous, we analyze the dynamic degradation of porous magnesium under simulated environment of human cancellous bone, and 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 uh, and we managed to publish it in Corrosion Science, one of top journal in this particular field. Again, what we analyze are the simplified cancellous bone, if you like, you know, simplified cancellous bone. So we take magnesium block and we create holes. Yeah, we create holes, and then we analyze the corrosion aspect of this porous magnesium after 24 hours, after 48 hours, and after 72 hours, and you can see that it's corroded there. It's degraded. So again, if we want to, if we can somehow create, um, if you can design a porous magnesium that once it is dissolved, the bone also heal completely. So that would be interesting, you know. At the end of the day, we want the bone to heal. We want stability, you know. We need stability in order for bone to heal. But if we can somehow design or develop a material with an implant that can provide the stability initially whilst the bone heal, and then once the bone completely heal, the implant also dissolve completely. Wow, that would be interesting, isn't it? Yeah. So this is for our research work on porous magnesium. Uh, right. This is it. You know, our attempt at simulating the real cancellous bone. The real cancellous bone is the one at the far end, the far right, number 8 there. That is the actual cancellous bone. Yeah? And then so we collect data in terms of porosity, you know, permeability, you know, density, you know, all sorts of measurements related to the actual cancellous bone. We embed into our simplified cancellous bone, if you like. So there are 7 different design of cancellous bone that mimics the actual cancellous bone. I know that the cancellous bone is unstructured, but this one is extremely structured. But as far as the porosity is concerned, it's the same. You know, the density is concerned, is the same. Yeah. So we managed to find exactly the same properties of the cancellous bone, and we turn that into a simplified, structured cancellous bone. So there are 7 of them there. And then we compare again permeability studies. This is a permeability study of cancellous bone and its idealized structures. So we compare between prismatic plate-like, prismatic rod, tetrachydicahedral rod, uh, with the actual cancellous bone from the neck of femur, from the greater trochanter. Uh, so you know that because cancellous bone, the density, the porosity varies, the structure varies from bones, from skeletal sites. So the one that you take from the spine, for example, is different with the one with the cancellous bone that you have in the greater trochanter of the femur, for example. Yeah. So this is extensive study by Dr. Ardian Shah, who is currently the director for Meditech. Right, right. Right, magnesium, calcium, bismuth alloy. Again, as I mentioned just now, some of the team members are so obsessed with magnesium, and of course, you know, magnesium easily degrade. And then, is it possible? Can we combine and turn it into a stronger, less degradable magnesium? You know, by adding calcium and bismuth. Well, yes, we managed to develop this type of alloy, magnesium calcium bismuth alloy, and then in order to improve its degradation rate or prevent it from degrading easily, we coat with nano aluminium and PCl, polycaprolactone. And these are the results. So again, you know, if you can somehow prevent magnesium from degrading easily initially, at the initial stage, we don't want magnesium to degrade while the bone heals. But then we want magnesium to degrade. So if we can have something like a very light coating on this magnesium calcium bismuth alloy, that would be super. Another work on magnesium calcium bismuth alloy. Now this time around we use silicon biopolymer coating to coat this magnesium calcium bismuth alloy. Another research work on magnesium. This one is magnesium hydroxyapatite magnesium oxide nano composite. And we see the effect of magnesium oxide on the biodegradation, physical properties and biocompatibility of magnesium hydroxyapatite magnesium oxide nanocomposite manufactured by Powder Metallurgy. This one, another magnesium project, and this time around we use fluorine to dope magnesium alloy. So deposition of nanostructured fluorine doped hydroxyapatite polycaprolactone duplex coating to enhance the mechanical properties and again corrosion resistance of magnesium. So you can see that we can get apatite growth, you know. So immersion. So you have the magnesium substrate with the porous PCl, polycaprolactone, and then the dissolution of the PCl and the emergence of magnesium hydroxide. And then you have the deposition for calcium phosphate base material and its growth. We had one this project on cobalt chromium. We're not really into cobalt chromium, but we have this one project on cobalt chromium alloy, novel hydroxyapatite composite reinforced with titanium nanotubes. So HA with titanium nanotubes. All right, okay. This is a research work from my student Mahdi Tahiri. Mahdi Tahiri, he managed to identify the use of shallot. You know, shallot apa? Bawang merah. Shallot and apricot tree gum. We use shallot and apricot 3 gram to reduce silver into silver nanoneedles. This is interesting. Silver nanoneedles. And we managed to find the right recipe, the right recipe in order to produce these silver nanoneedles. Rice husk. Rice husk derived bioactive glass ceramic as a functional bioceramic, synthesis, characterization, and biological testing. We published this in Journal of Non-Crystalline Solids. We have lots of rice husk, especially here in Malaysia. So we try and utilize this rice husk and convert them into bioactive glass ceramic. Barium fluoride, doped hydroxyapatite, another work on hydroxyapatite, doping of hydroxyapatite with barium and fluorine. And we look at the in vitro bioactivity of this barium fluoride doped hydroxyapatite. We have another doping of hydroxyapatite with erbium. Yeah. And this one we publish in Journal of Alloys and Compounds. And so successful development of erbium doped hydroxyapatite. And this one is on kanaf fibers. Again, Malaysia produce lots of kanaf. We have lots of kanaf fibers, and we can. One of our students, Dr. Saiful, utilize kanaf fibers and try to see how the growth of hydroxyapatite on kanaf fibers. So that's the picture of the untreated kanaf fiber, and then after mercerization, and then the immersion under simulated body fluid, and after 7 days we can see some hydroxyapatite formation on the kanaf fibers, which of course require further research. This one, polydopamine, yttria, stabilize, zirconia, quinone-rich polydopamine functionalization of YSZ for appetite biomineralization, the effects of coating temperature, published in Applied Surface Science. And we also have a PVA hydrogels with halosite, PLA polyaniline scaffold. This is a scaffolding using polymer-based material, PLA and polyaniline. We also have calcine silica aerogel work, and that's it. We also have some work on smart biomaterials that responds based on heat. Yeah. And this is my final slide, and time is 3:48. Acknowledgements. These are the things that I presented to you today are all the work of my students that I supervise. So these are all of them, yeah, or maybe missing a few, yeah. But these are all my PhD students. You know, Dr. Ali, Amir, Arafat, Ardi, Arman, Aziz, Badar, Daud, Farnas, Fatihi, and the rest. And we also have our master students. So these are all our master students who, you know, some of them work like a PhD student. So thanks and congratulations to all of them. And that's it. And time is 3:50. Excellent. Back to you, Fatiha.
Thank you very much, Dato, for your very interesting presentation and very